Okay. Good morning, students. Yesterday we have started the fifth semester. Okay. In that I have told in the introduction I have told about four blocks. About the four blocks and what are the topics covered in the four blocks. And even I have given the introduction of all the units. Okay. So first unit, today we are starting with the first unit. It is vector spaces and subspaces. Okay. I hope so you are able to see the blackboard. Okay. So here I have given the introduction of the vector space. That is, I have given the definition of that one. So vector space, the definition is starting whatever the theory part is there that I have not written. It is a V is a set of vectors, and if F is the field of scalars, okay, V is the set of vectors here, and if you take F, it is the field of scalars. Okay, so whenever this is the set of vectors and F is the field of scalars, then V of F, okay, is called as a vector space. V of F. So with respect to set of vectors and field of scalars, we'll write it as V of F. So it is called as a vector space. So the 6 conditions are there. So first condition is V comma plus is an abelian group. Second one is if A belongs to F. F means here field of scalars. Okay. Alpha bar belongs to vectors, implies A into alpha. If you combine these two, that is your scalar multiplication you are doing. If you do the multiplication of these two, whatever the resultant you are getting, that should belongs to the set of vectors. Okay. So this is the second property. And third one is A into B alpha bar equals to AB into alpha bar. For all, here A and B are field of scalars and alpha bar is set of vectors. Okay. So A into alpha bar plus beta bar equals to A into alpha bar plus A into beta bar. Okay. This is the fourth condition. Here same A is the field of scalars and the alpha comma beta are set of vectors. Okay, so this is called as associative property with respect to multiplication, scalar multiplication. Okay, so these two are the distributive laws. Okay, and last one is the unit is the identity, multiplicative identity. So when you multiply this one, that is I is the here multiplicative identity which belongs to field of scalars. That means whenever the scalars are given, if in that one is present with the, when you multiply that one with the set of vectors, that is alpha bar, you will get it as 1 into alpha bar equals to alpha bar. So we all know that whenever any element, if you multiply with 1, you will get the same element. Okay, so if that element belongs to V, that means if it belongs to the set of vectors, then this sixth property is satisfied. Okay, so here whenever it is a V comma plus is an abelian group. So I have told already that when it is an abelian group, the conditions will be, so first one will be closure law or closure property. Second one will be associative property. And the third will be additive identity. We are doing with respect to of addition here. V comma plus is there. So the binary operation is here plus. So it is called as additive identity. And fourth one is additive inverse. And the fifth one is commutative law or commutative property or commutative axiom. Okay, so we call them as, so to any set to become as an abelian group, these 5 conditions it has to satisfy. If these 5 conditions are satisfied, then the set V is V comma with respect to of the operation plus, it is called as an abelian group. So for first condition to become any V of F as a vector space, this condition it should satisfy. Okay, you can take like this alpha, beta, gamma elements. So if we'll take the example of anyone, whether the elements are complex numbers or whether they are the real numbers. Okay, so if we'll take complex or real numbers, here alpha and beta are there, no? So direct we are not taking the alpha. The alpha you are writing as like this. That is alpha is equals to A1, A2, A3 up till AN elements. Beta equals to B1, B2, B3 up till Bn. And gamma is equals to C1, C2, C3 up till Cn elements. So to satisfy all these properties, we need alpha, beta, gamma. Okay. In some problems already they will mention alpha, beta, gamma in some manner. Okay. So through that, if you substitute those values alpha, beta, gamma, then you can make all the satisfaction of all the properties. Okay. And one thing is, the best example to satisfy all the 6 properties is that it is the zero vector. Zero vector satisfies all the properties. Okay. So if you're having the set of vectors only one element, that is 0. So if you put like this, it is a vector. So zero vector satisfies these all 6 properties. So the set 0 is a vector space. Okay. So you can see here, closure means addition of 2, that is alpha plus beta. If it is with respect of binary operation plus, no. So if alpha is this one and beta is this one, when you add both of them, you will get A1 plus B1, A2 plus B2, comma A3 plus B3, so on up to AN plus BN. So the combination of these two will be in set of vectors V. Therefore, so closure property is satisfied. So associative property means you will have alpha plus beta plus gamma is equals to alpha plus beta plus gamma. That is A plus B plus C is equals to A plus B plus C. Okay. So it satisfies when you add these two, that is alpha plus beta plus gamma. So you will get the elements that will be in the form of V. So it satisfies even associative property. When it is the additive identity means it should be in the form of 0 plus alpha bar equals to alpha bar plus 0 equals to alpha bar, where 0 is called as the additive identity. Okay. So this is the additive identity. And whenever it is the additive inverse is there, means whenever alpha bar belongs to V, there exists compulsory minus alpha bar belongs to V, such that additive inverse, whatever here additive inverse is there, that will be in the form of alpha bar plus minus of alpha bar. It is equals to minus alpha bar plus alpha. So it is equals to 0 vector. Okay. So this is the additive inverse. So alpha means here you have A1, A2, A3 up till AN. So you can take minus of this one means minus A1, minus A2, minus A3 up till minus AN. So when you add this positive values and negative values, compulsory you will get the 0 vector. So it is satisfying the additive inverse also, where the identity element is 0 bar. Okay. So when it is a commutative law, you will have alpha plus beta equals to beta plus alpha. So in between you have the sign is plus. So whether you add this to that or that to this, you will get the same one. So it satisfies even the commutative law. Okay. So when any you are taking alpha, beta, gamma in this form and it is satisfying all these 5 conditions, first property is satisfied. So abelian group. Second one is you can take A belongs to, A is any field of scalars. You are multiplying that one. And alpha you have A1, A2, A3, AN. You are multiplying A into alpha means A into A1, A2, A3, AN. When you multiply that, you will get A1, comma A, A2, A3, AN, which belongs to the vectors V. Therefore, it satisfies this property also. And when you take out this one, this is the A into B of alpha. A and B are here scalars. When you multiply this one, B with respect of alpha bar. So that means just you are interchanging this one, you are taking outside B means you will get AB of alpha bar. So this whatever the alpha, beta, gamma you are taking, it satisfies all the conditions. So we can tell that it is the vector space. So in the examination for the 5 marks question, they will ask define what is vector space and give some examples. So in your textbook, some examples are given which functions or which sets are forming the vector space. Okay, try to practice those example problems. So this is about vector space. Next thing here is second one is the subspace is there. Okay, next one is subspace. So for subspace, you have first main thing, one definition is there. After that, you have the necessary and sufficient conditions are there. So three conditions are there. With the help of those three conditions, any problem is given, you can solve them. With the help of those conditions, you can solve the problems, and you can show that given whatever the subset is there, that is the subspace of V. Okay. So here subspace, how you have seen in group, subgroup, or in rings, subring. Same, the similar definition will be there for subspace also. Here, if you take any subset, okay, you are taking one set W, which is subset or equals to V. Here V is the vector space, V is the set of vectors. Okay, so you are taking W such that it is subset or equals to V. So to become this subset as a subspace, so W to become a subspace, it has to satisfy the conditions of all the vector space. Okay, any subset to become a subspace, it has to satisfy all the conditions of the vector space. That means first one is V comma plus abelian group, second one A into alpha belongs to V, and third one distributive laws, and fourth one is the associative law, and fifth one is the that is 1 into alpha equals to all the 6 properties. If this W also satisfies, then this W is called as a subspace of V. Okay, this is the actual definition of the subspace. So it is a very lengthy process to solve all the 6 properties and show that it is a subspace. So that's why 2 necessary and sufficient conditions are given. So with the help of that, just if you show those 2 necessary and sufficient conditions, automatically we can tell that W is the subspace of V. Okay, no need of finding all the 6, not even 6. Those 5, V comma plus abelian group means 5 properties will be there, and here again 4 properties. So 9 properties we have to show actually. So no need of showing those 9 properties. Just if you show these 2 necessary and sufficient conditions, then you can tell that W is the subspace of V. Okay. So you have the definition of subspace. First one is let V of F be a vector space and the W is subset or equals to V. Okay, then W is said to be subspace of V if W itself is a vector space over F with the same operations. Okay, with the same operations of vector addition and scalar multiplication. Okay, this is the actual definition of the subspace. So that is let V of F be a vector space and W is subset or equals to V. Then W is said to be a subspace of V if W itself is a vector space over F. This, whatever the sentence is there, it tells that W has to satisfy all the 9 properties. Then only it is called as vector space. So with the same operations of vector addition and scalar multiplication. Okay. So this is the actual definition of the subspace. So this is the lengthy process. So we are having the necessary and sufficient conditions. So with the help of that, you can tell that whatever the given subset is there, that is becoming the subspace of V. Okay. So the first necessary and sufficient condition is let V of F be a vector space. Here I am writing the shortcut of vector space as V dot S. Okay. Vector space, and let W is subset or equals to V. The necessary and sufficient condition. Sufficient condition for W to be a subspace of V, or first one is alpha bar comma beta bar belongs to W implies alpha bar minus beta bar belongs to W. This is the first condition. Okay. Second one is A belongs to F and alpha bar belongs to W implies A into alpha bar belongs to W. Okay. This is the second condition. So here one more necessary and sufficient condition is there. First necessary and sufficient condition is let V of F be a vector space and let W is subset or equals to V. The necessary and sufficient condition for W to be a subspace of V. Okay. So first condition is if alpha and beta are there, they belongs to the subset W, implies the difference of these two vectors. Okay. W means here it is a vectors, no? So the difference of two vectors, whatever the resultant you are getting, if that also present in W, the value, if you take alpha as before problem, we have taken A1, A2, A3 up till AN, and beta as B1, B2, B3. If you do the subtraction of those two, you will get A1 minus B1, A2 minus B2, A3 minus B3. So whatever the resultant you are getting, if that value also belongs to W, then first condition is satisfied. And the second condition, if A is the field of scalars, okay, that means you are taking any number. Scalars means here 1, 2, 3, 4, like that, anything. Okay. So alpha bar is again A1, A2, A3 is there. So if you multiplying 1 into alpha bar values, A1, A2, A3. So you will get the same alpha bar, no? So A into 1 into alpha bar means you will get alpha bar only. So when you do the scalar multiplication of these two, whatever the resultant you are getting, if that belongs to W, then W is called as a subspace of V. Okay, this is the definition of subspace. So if any problem is asking is to show that W is a subspace of V, then with the help of these two conditions, we can tell that W is a subspace of V. Okay. So no, with this help definition, you have to show all the 9 properties. But with this necessary and sufficient conditions, if these two properties are satisfied, it is enough to show that it is a subspace. So this is one necessary and sufficient condition, and one more is there. So these are all with the help of any conditions, you can show that W is the subspace of V. Okay, second necessary condition is let V of F be the vector space and vector space, and here a non-empty set W is subset or equals to V. So the necessary, so here I am writing the shortcut necessary and sufficient condition for W to be subspace of V. Okay. So for it is if A comma B belongs to F and alpha bar comma beta bar belongs to V. Okay, W. We are taking the subset, no? So W implies A alpha bar plus B beta bar should belongs to W. Okay. So actually, whatever these two conditions, necessary conditions are there, they are the theorems in your unit. Okay. Whatever the first unit is there, in that the proof of these two conditions is also there. Okay. That's why these two are given as the theorems. Okay. So your second one is let V of F be a vector space, a non-empty set. A non-empty set W subset or equals to V. So these two conditions, then the necessary and sufficient condition for W to be a subspace of V is, that is, if A comma B are the two elements which are from the field of scalars. Okay, F represent here field of scalars and alpha comma beta belongs to set here subset W. Okay, which is the subset of V. Okay, so it belongs to the here we can tell set of vectors. Okay, so then combination of these two field of scalars and also vectors you will get as A alpha bar plus B beta bar belongs to W. Okay, so first thing is to show that any set W which is subset or equals to V, to tell it as a subspace of V, first condition is first one 9 properties you have to show. So it is a very lengthy one. Next one, second one, we have necessary and sufficient. In these two conditions are there. So if it is also difficult, then we have the third condition. Means even if we'll show first one, second one or third one, then compulsory if it satisfies, then we'll tell W is the subspace of V. Okay. Third one only only one condition is there. That is A alpha bar plus B beta bar belongs to W. So if we'll show this also, then also W is called as a subspace of V. Okay. So, and one more condition is there, same necessary and sufficient conditions. So these all proofs, whatever the necessary and sufficient conditions I am telling, these are the theorems. So in examination, they may ask for 5 marks questions. Whatever the necessary conditions are given, those proofs are there in your textbook. So try to practice those proofs. Okay. And last one is a non-empty set. A non-empty set W is a subset of vector space V of F. Then W is a subspace of V. W is a subspace of V if and only if A belongs to F and alpha comma beta bar belongs to W, implies A alpha bar plus B, that is beta bar should belongs to W. So this is the third necessary. Here if and only if is there, no, that means you have to prove this is equals to this one, and that is W is a subspace of V when this condition is satisfied. Okay, this is the third condition. Even you can take the second condition, A alpha bar plus B beta bar belongs to W, or third condition is if A belongs to field of scalars and alpha bar and beta bar belongs to subset V, subset W, then the combination of these two, that is here you have B, no, instead of B you have only one scalar, that is A. So A into alpha bar plus beta bar belongs to W. So for this also you have the proof. Okay, these all whatever the conditions I am telling, these are the theorems. Okay, so we'll see one example of a subspace. So how we can tell any given condition will be given in the question, no? With the help of that, how you can tell that W is a subspace of the vector space V of F. So if the question will be given like this, if we'll take the example of subspace, the set W of ordered triads you have in the form of x comma y comma 0, okay, where belongs to field of scalars is a subspace of okay. So V3 means here the whatever the vectors are there you have here with respect of 3, that is the three coordinates will be there. So that's why it is in the form of x, y, 0. So of field of vectors V of F. So here whatever the values are given, those are in the form of x comma y comma 0, where x comma y belongs to field of scalars. You have to show that this W is a subspace of V of 3. Okay. The solution for this one is, so first you write let alpha. So we can take the third condition is there, no? Third condition is A alpha bar plus B beta bar. If it belongs to W, then this W is the subspace of V. With the help of this necessary and sufficient condition, you can solve this problem. Okay. So here A alpha bar plus B beta bar should belongs to W here. What is our given W? It is in the form of x comma y comma 0 here. Okay. So first you write let alpha bar comma beta bar belongs to W. So here where alpha bar is equals to x1 y1 0 and here beta bar equals to x2 y2 0. Okay, so we need two set of vectors here. First one is alpha bar and second one is beta bar. These are in the form of like this. Okay, x y 0. So for 2 you can't take x y 0 no. So that's why we are taking alpha values as x1 y1 0 and also beta values are x2 y2 0. Okay. Here you write for some x1, y1, x2, y2 belongs to F. Okay, these are from scalars. So while telling the introduction, already have told the elements present in the coordinate are called as a scalars. And when you put the bracket for those scalars, we call them as a vectors. Okay. Inside elements are called as a scalars. That's why here we are writing x1, y1, x2, y2 belongs to F represents the field of scalars. Okay. So for this you write let A comma B belongs to F. Okay. Therefore A alpha bar plus B beta bar. So this is the condition, no, necessary and sufficient condition to show that W is a subspace. So to prove this problem, we are writing here first let alpha bar and beta bar. So the necessary condition we need alpha bar and beta bar. So these two belongs to subset W. So here where alpha bar equals to, the given question is in the form of x, y, 0. So you are taking alpha bar as x1, y1, 0 and beta bar as x2, y2, 0. So these whatever x1, y1, x2, y2 are there, they belongs to field of scalars. So to prove this condition, we need A and B. So let A comma B belongs to field of scalars. Therefore, to prove that this belongs to W. So what is W? W is this one. So A into alpha bar plus B into beta bar. So here A is the scalar, no? So scalar multiplication, you put A. So what is alpha bar? Here we have defined alpha bar is equals to x1, y1, 0 plus b into what is beta bar? Beta bar is x2, y2, 0. Okay. Now you add this one. You will get it as, if you multiply this a into this one and b into that one, you will get a into x1, a into y1. This is 0. Okay. Plus b into x2, b into y2, and b into 0 is 0. Now you add this both. You will get a x1 plus b x2, next a y1 plus b y2, 0 plus 0. Okay. So whatever the resultant we got here, that is a x1 plus b x2. This whole thing is 1. And this whole thing is 1 and last is 0. So it is again in the form of C. It is in the form of X. This is Y and this is 0. Okay. So when you do A into alpha bar plus B into beta bar, whatever the resultant you are getting, that resultant is in the form of X comma Y comma 0. So therefore this resultant will belongs to W. What is W? W is this one. And the answer you are getting the same. So therefore A alpha bar plus B beta bar belongs to W. So W is a subspace of V3 of F. Okay. So like this you have to do the proof for any given problem to show that it is a subspace of the vector space. Okay. So here you can write clearly x1 plus bx2 comma a y1 plus b y2, it is belongs to, because inside the coordinate whatever the elements are there, those will be for the field of scalars. So whatever the elements are there in the coordinate, those you are able to see here. No, I am writing here. So after this, clearly x1 plus b x2 comma a y1 plus b y2 belongs to field of scalars. Okay. And here alpha bar comma beta bar belongs to W. Okay, this is satisfying the conditions. So we can tell implies A alpha bar plus B beta bar belongs to W. This A alpha bar plus beta bar, this whatever the condition is there, it is belonging to W. So therefore W is the vector space of, here last we can write, hence W is subspace of, W is subspace of V3 of F. Okay, this is the solution of the problem. So like this you have to I hope so. Now you are getting the screen, whatever clarity is there. Okay. Some blurriness is coming, but you are able to see all the whatever the board I have written. Okay. So we have taken the example of subspace to show that any given subset is a subspace of the vector space. So the set W of order triads x comma y comma 0. So it is in the form of x comma y comma 0. You have to show that where the scalars are x comma y, they belongs to F, is a subspace of V3 of F. So for this you are taking the second condition or second definition of the subspace. If A comma B belongs to F and also alpha bar comma beta bar belongs to W, then A alpha bar plus B beta bar belongs to W, then we call W as a subspace. For that we are selecting, let alpha bar and beta bar, they belongs to W, and alpha bar is given in the question. So you are writing in that form x1 y1 0, x2 y2 0. So in this, inside whatever the elements are there, they are the field of scalars. So you are taking the scalars. Why? Because subspace definition is in the form of A alpha bar plus B beta bar. So A comma B belongs to F So we are taking A into alpha bar plus B into beta bar. So A into alpha, this value, B into beta. So when you do the scalar multiplication and when you add that, whatever the resultant you are getting, that resultant is in the form of the given. So it belongs to W. Therefore, W is a subspace of V3F. Okay. So like this, you have to solve the subspace. So after the subspace, you have the linear combination of vectors. Linear combination of the vectors. Okay. Linear combination of vectors means we have seen already any set S is there. So if you write that say alpha 1, or if you take alpha comma beta comma gamma. Okay. So set S is there, you having the elements in as alpha, beta, gamma. Okay. And you are taking that alpha. Only alpha is there. No alpha, you can take it as alpha 1, alpha 2, alpha 3, so on, alpha n. Okay. So this whatever the alpha is there, it belongs to the V, vector space V. And if you are taking x1, x2, x3, whatever up till xn are there, they are the field of scalars. Okay. So these belongs to V and these belongs to F. So when you combine these two, or when you do the scalar multiplication of these two, you can take x1 by x2, x3, or you can take a1, a2, a3, so on of an belongs to F. So when you take the combination of these two, that is a1, x1, a2, x2, so a into alpha 1, a into alpha 1, a into alpha 2, so on up till an alpha n. Or if you take x1, a1, x1 plus a2, x2, and so on up till an xn. Okay. That means whenever you are taking the vectors and also whenever you are taking the field of scalars, when you do the scalar multiplication of those two and you add them, okay, whatever this resultant you are getting, this is called as a linear combination of vectors. Okay. So here whatever the elements are there and the elements which present in V and also F, if you do this is a1 into alpha 1, it is called as scalar multiplication. So when you do the multiplication and you add them, this is called as a linear combination of vectors. So if you understand the linear combination of a vectors, then you have the same for this one related one, you have linear span is there. So for the linear combination only, you have the topic, you have linearly independent vectors and also linearly dependent vectors. So the concept knowing the linear combination is very important. Okay. So if you take any vector here, yes, such that it is in the form of like this alpha 1, alpha 2, alpha 3 up till alpha n. Okay. So next you can take same beta 1, beta 2, beta 3 up till beta n, gamma 1, gamma 2, gamma 3 n. So like this, if you take all the vectors and if you multiply them with scalars, the scalars may be a1, a2, a3, x1, x2, x3, or even scalars will be numbers. No, you can take 1 comma 1 comma 1 or 1 comma 0 comma 1, 1 comma 2 comma 3, like this, any scalars. If you multiply these scalars with the vectors and if you add them, that is called as a linear combination of the vectors. Okay. So linear combination, you have definition is there in your textbook. So on that you are not having any theorems, just it is the main important linear combination for linear span. Okay. So linear combination here, the definition is let V of F be a vector space if alpha 1, alpha 2 up till alpha n, these belongs to vector space V then any vector okay, then any vector gamma equals to a1 alpha 1 plus a2 alpha 2 up till an alpha n, where a1 comma a2 comma a3 up till an belongs to f. Okay, is a linear combination of, we can write shortcut as linear combination of vectors alpha 1 alpha 2 so on. This is the actual definition of the linear combination of the vectors. Okay, so let v of f, okay, v of f means v is the set of vectors, f is the field of scalars. So v of f be a vector space. Vector space means it is satisfying all the 9 conditions if alpha 1 alpha 2 up till alpha n belongs to v. So this means these are the vectors. Then any vector, so whatever I have told, scalar multiplication of scalar and vectors, scalar and vectors, scalar and vectors. If you write this all in another set, here the set is gamma. Okay, so whatever the combination of these scalars and vectors are there, if you write as another set as gamma, then this is called as, this is the representation of linear combination of vectors. Okay, that is gamma equals to a1 alpha 1 plus a2 alpha 2 up till an alpha n. Instead of a1 you can take x1 y1, anything you can take, those are the scalars, no? So this is called as where a1 a2 a3 an belongs to field of scalars is a linear combination of vectors. These are scalars and these are vectors. Okay, this is the definition of the linear combination of vector. So on this you have the problems also will be there that you have in practical, whatever the lab is there, no, mathematics. In that practical classes you will know how to find the linear combination of vectors. So any alpha value will be given. So alpha value will be given means you have to write that alpha value as a linear combination of vectors. So the question will be like this, see, express the vector alpha equals to 1 comma minus 2 comma 5 as a linear combination of vectors. Here the vectors are given as e1 equals to 1 comma 1 comma 1 and e2 equals to 1 comma 2 comma 3 and e3 is equals to 2 minus 1 1. 2 minus 1 1. Okay, so the problem will be asked like this for you. Express the vector alpha equals to 1 minus 2 5 as a linear combination of vectors. Here the vectors given are e1 e2 e3. That means here it is given now the gamma, whatever gamma is there, that is here alpha here. That gamma value is 1 comma minus 2 comma 5. So you have to write it is equals to a1 into alpha 1. Instead of alpha 1 we have e1. That is a1 into e1, a2 into e2 plus only here 3 are given. This is for n terms we are taking. So only here 3 terms are there. So a into e1 plus b into e2 plus c into e3. So when you add them and when you equate it to alpha, you will get the a, b, c values. So that is only called as a linear combination of the vectors to find that one. Okay. So if you solve this problem, Are you able to see? Yeah. Good. Blurry. So for this, if you'll take, I'm writing here solution. Okay. Let alpha, what is alpha value given? 1 comma minus 2 comma 5 here. So we are writing this alpha, that is gamma is equals to A1 into alpha 1 plus A2 into alpha 2. Similarly, alpha, this value is equals to, you can take ABC or XYZ, anything you can take, okay? X into E1 plus Y into E2 plus Z into E3. So you are writing alpha as a linear combination of this one. So it is equals to X into what is E1 value given? It is 1 comma 1 comma 1. And Y into what is E2 value? 1, 2, 3 plus Z into E3. 2 minus 1, 1. So now you do the scalar multiplication. So you'll get it as this is X. Directly if you add. So one step you can write it as X comma X comma X, Y comma 2Y comma 3Y, and 2Z minus Z comma Z. And then you add. You will get the same one. So here you can take first is X plus Y plus here it is 2Z. Okay. Next here X plus 2Y minus Z. Next X plus 3Y plus Z. Okay. So this is the addition of this one and the scalar multiplication. Now this X plus Y plus 2Z and X plus 2Y minus Z, X plus 3Y plus Z, you equate with this one, that is 1 comma minus 2 comma 5. Why? Because this is the linear combination of this one. So you will get here so X plus Y plus 2Z equals to 1. X plus 2Y minus Z equals to minus 2. Plus 3Y plus Z equals to 5. Okay. So directly you can put them as equation 1, 2, 3 and you can solve them and you can find what are X, Y, Z values. Okay. That is one procedure, and another procedure is with the help of you're writing this one as the AB augmented matrix. In the matrix form you can convert, and you can after the augment matrix it is converted into a Boolean form. Then we can find alpha, that is X, Y, Z values. Or we can call it as Gauss elimination method also. Matrices, if we have idea. So with the help of the matrices also you can solve, or directly 3 equations by equating any one equal, then also you can find X, Y, Z values. So if you write this in the matrix form, you will get it as 1, 1, 1, 1, 1. Here 2 it is there. Okay. 2 and last value is this one, 1, 1, 2 minus 1, 1, 2 minus 1, and this value is minus 2. Next 1, 3, 1, 5. Okay, you are writing in the matrix form. So when you convert, when it is you are reducing the given matrix into a Boolean form, this whatever the triangle is there, this triangle you have to make zeros. That is called as echelon form. Okay. So reducing to echelon form. Okay. So for that, this has to become 0 and this has to become 0 and this has to become 0. First you make this as 0, then you make this, and after that this one. Okay. So for that, here you know that is elementary operations will be there. So to reduce any matrix, we will use the elementary transformations here. So for that, you are right. This is called as R1 row. This is R2 row, and this is R3 row. Okay. So this is R2 minus R1. So you are applying the operation as R2 is equals to R2 minus R1, and for R3 you are using R3 minus R1. Okay, so when you do this operation, you will get it as 1, 1, 2, 1. Next 1 minus 1 is 0. 2 minus 1 is 1. Minus 1 minus 2 is minus 3. Minus 2 minus 1 is minus 3. 1 minus 1 is 0. 3 minus 1 is 2. 1 minus 2 is minus 1. 5 minus 1 is 4. Okay. So for echelon form, you need to even convert this 2 as 0. So you can do this as with the help of y, because you can't do this and this subtraction. Again, you will get 1. So here 0 is there already. So we can take R3 and R2. So you can reduce it as again next operation is R3 minus 2 R2. Okay. So what the matrices will become 1, 1, 2, 1. Next second row like that only. Next 0, 2 minus 2, 0, minus 1, minus of minus. So you will get 5. Okay. So this is minus 1, minus of minus 2 is there. So 3 2s are 6. 6 minus 1 means you will get 5. Next 4 minus of minus plus 6. You will get it as 10. Okay. Now we have converted this as echelon form. So if the triangle becomes, this is the triangle now 0, 0, 0, then it is called as a echelon form. Now you can write them as equations. That is x plus y plus 2z equals to 1. Next, this is x value is 0. What is y? Y minus 3z equals to minus 3. Next, 5z equals to 10. So you will get here z value as 2. So we got z value as 2. No, you can, if you substitute in that, you will get y value. Z equals to 2. Substitute z in 2. You will get y minus 3 to the 6 equals to minus 3. Implies y equals to 3 you will get. So substitute y comma z in 1. So we get x equals to all x is minus 6 you will get. So we got x, y, z values. Okay. So now so this is the answer. Whatever the alpha beta values are there, that you will get the values. Therefore, hence alpha is equals to x into, no, that is minus 6 into E1 plus y value is 3 into E2 plus z value is 2 into E3. So this is our alpha value. That is whatever the combination you have written, alpha is the linear combination of this one. So like this linear combination problems you have to solve. So they may ask for 5 marks questions. Even practical problems also they are asked in the examination. So while you are going to the practical classes, whatever the problems are there on linear combination and also subspace, those will be asked even in your theory examination also. Okay. So instead of these problems, you have theorems in your textbook. So when you will get your textbooks, so try to see all the theorems, conditions, whatever I have told, the subspace conditions are there, no? Those are the theorems. Proofs are important. Okay. So whenever you know the linear combination, next one is the linear span is there. So we'll represent the linear span as L of S. Okay. L of S is called as a linear span of S. Here the S is the set. Okay. So S is subset or equals to V. So S is any set which is subset or equals to V. So when if you write the all the linear combinations, okay, set S, if you have in the form of alpha, beta, gamma. Okay, so with the help of this set S, you are taking alpha, beta, gamma. With these only, this is the finite set, only 3 elements are there, alpha, beta, gamma. With these alpha, beta, gamma, you can write infinite number of linear combinations. Okay, here the vectors are only 3 vectors are there, but scalars, you can take any scalars, no? So this you can write it as alpha is equals to 1 into alpha 1 plus 1 into beta 1 plus 1 into gamma 1. So next, if you take beta is equals to 1 into alpha 1 plus 0 into beta 1 plus 1 into gamma 1. Next, gamma is equals to 1 into alpha 1 plus 2 into beta 1 plus 1 into, you can repeat them now. So that means when you multiply this alpha, beta, gamma with the scalars, there are, so if you take 1 to infinite, many number of scalars are there. So you can multiply those scalars and you can write all the some other set, alpha, beta, gamma, you are writing some other sets as a linear. What is linear combination? Scalar into vector, scalar into vector, scalar into vector. So finite number of sets in a set, yes, you can have infinite number of linear combinations. If that infinite number of linear combinations, if you put in any set, you think that it is equals to delta. So delta equals to here alpha, beta, gamma. You may have X, Y, Z, T, U, V, so on like this. These are all the linear combinations. So whenever you put all the linear combinations as one set delta, so that set is called as a linear span of set S. Linear span is nothing but the possible linear combinations. If you put them in the set, that is called as a linear span. Okay, so the definition of linear span. Linear combination means scalar multiplication of scalars and vectors. If you put the plus sign in them and if you write that combination as one set, it is called as linear combination. Here linear span means infinite number of linear combinations. If you put as one set, that is called as a linear span. Okay, so you have the definition in your textbook. It is in the page number 7. You have, let V be a vector space over a field F and SC subset or equals to V. Define L of S equals to, see, you can write here SC subset or equals to, I'm giving the definition here. So with the linear span, you have many theorems are there. This is the last topic in first unit, linear span. So on linear span L of S, you have many theorems are there. And the definition is, let S be a non-empty set non-empty subset of a vector space V of F, the linear combination, okay, the linear is the set of all possible linear combinations of all possible finite subsets of, okay, this is the main definition of linear span. So we'll represent, and if you write in this form, L of S is equals to A1 alpha 1 plus A2 alpha 2, A3 alpha 3, so on up till AN alpha n, such that all AIs belongs to F and alpha I's belongs to S. This is the main definition. Okay. L of S equals to, this is the linear combination. A1 alpha 1, A2 alpha 2, A3 alpha 3, where AIs belongs to scalars, alpha I's belongs to the set of vectors. So this is the definition of linear span. let S be a non-empty subset of V of S. Just I have written SC is subset or equals to V. That is only the sentence. The linear span of S is the set of all possible linear combination of all possible finite subsets of S. Okay. Whatever I have explained, that is all linear combinations. If you write as one set, that is called as a linear span. Okay. So here for this, some important note is there for linear span. If SC is finite, then L of S will be infinite. Why? Because here only if 3 elements are there, you can write that 3 elements as any number, infinite number of linear combinations. So it is infinite. So these are the 1 mark questions. In multiple choice also, they will ask this one. And second one is if L is SC is subset or equals to V, implies L of SC is also subset or equals to V. And third one, SC is if it is empty, means no elements, then compulsory one linear combination you will get, that is with the 0 element, 0 bar or 0 vector. Okay. So this is about the linear span. And on linear span, you have important theorems are there. That is in the page number 7, 1.3.10. So these are all the theorems. And page number 8 also, you have the important theorems. And 9. So almost I have told linear algebra means compulsory. You will have the theorems only. Okay. So if you know the definitions, then easily you can solve the theorems. So that's why the definitions of each and every term are important. So already today 2 classes we have completed yesterday and today, and more only 3 classes are there for linear algebra. We'll see the 3rd block and 4th block. Okay, those are somewhat problematic. You may not get bored, because definitely if you'll see the 1st block and 2nd block, all the definitions will be there and theorems will be there. So you may not understand exactly. And see, today I thought of completing some theorems, but we are not unable to complete. Why? Because one theorem will take 1 class. So only 5 theorems we can complete. That also from the unit 1 only we can complete. So that's why just I will, if you have the textbooks, you take the important theorems and you try to practice them. In next class, we'll see the block 3 and block 4. Matrices are there, no? In that matrices, you have linear equations are there. Cayley-Hamilton theorem is there. Verification of Cayley-Hamilton theorem. Those are also 10 marks questions and also 5 marks questions. So 3rd block and 4th block, they are problematic. So you may not get, you will be easily understand those problems and you can do in your examinations. And last day we'll see the important questions in linear algebra. And we have to start even 3D also. So we have to complete that one. So that's why I'm not going into the theorems. If we'll go deep into the theorems, we may not complete the syllabus. Okay. So our next class, 12th, we'll see. Okay. Bye, students.
Thank you, ma'am.